All right, so here's maybe an interesting situation, but something that on one hand is going to look very, very particular and very specific, but on another hand actually gives us a very general fact about the relationship between antiderivatives, integrals, and derivatives. So here, let's imagine you're given some function. Here we're going to phrase it in terms of the variable t, but so be it. Ultimately, we're just going to be looking at some function f. And let's define a function in terms of the area under the function we were given. So we were given the function f, and with that function you could start looking at the area under that function, well, the signed area technically, but you are aware of those particulars. And here, let's define g of x to give you back the area between some constant value c and x under your function. So what we're saying here is, like any function does, you put something in, you get something out. Put in x equals 10, you're going to get out the area between c and 10 under the function that you were given. Put in x equals 100, you're going to get the area between c and 100. So x here is the parameter that's changing. Our function of interest is fixed. Our constant that's going to be the one boundary of our interval is fixed. And here then, as x changes, the area under the curve changes, hence g changes. And an interesting question might be, what is the derivative of g? Since g is changing, can we capture its derivative? And the answer is yes, we absolutely can. So let's consider the integral from c to x of f of t dt. What is this? Well, this is capital F of x minus capital F of c. This is how you compute the area under the curve, right? Okay, well now, this is precisely our function g. But we're not interested in g, are we? No, we're interested in g prime. But what would g prime be? Well, g prime, of course, would just be the derivative of g. In particular, since g is a function of x, it would be the derivative with respect to x. And since g is just capital F of x minus capital F of c, then g prime is the derivative of capital F of x minus the derivative of capital F of c. Now, you know how a derivative attacks a sum. It just attacks it term by term. Now, what is the derivative of capital F? Well, capital F was your antiderivative function. So the derivative of capital F is going to be precisely little f. What is the derivative of capital F of c? Well, think about this. C is a constant. And no matter what our original function is, the antiderivative function is, yet again, a function. And so if you plug c into that function, now this is just a good old-fashioned number. Whatever c is, plug it into the antiderivative function, you're going to get some number out, and when you take the derivative of a number, that's going to be 0 and drop off. So the long story short is, when you have a function that is defined in terms of the integral, and you take its derivative, you get back the function that was inside. The derivative of the integral is the function that was left inside. Let me write that in full totality here. The derivative of the integral is the function that you started with. And you know that, right? Because you know that the integral is based on antiderivative, and you know that the derivative of the antiderivative would take you back to where you started, but this sort of articulates that in, well, a full scope with this particular function. And, well, I'm going to take a couple videos here fairly concisely to address a couple examples of how something like this might show up.